Hi, hello, my name is Samuel Garcia, and today I'm going to tell you about flattening the curve, okay? So, coronavirus, as you guys all know, is a virus that affects people, right? Now, at the start of this virus, it was a very small amount of people who got sick. And then, well, it slowly but surely increases, right? Then there's a point where, as right now in the last, move something, like the last 2 weeks, in places like New York and um, places like California, it's been increasing ever so slightly to a point where it's right here, right? This is not a number, but you could put let's say, I think it's like 400,000 at this point, I believe so. But it's an example of exponential growth. But something like a virus doesn't only use exponential growth, because if in the exponential growth exponential growth graph, it's only showing you like basically going infinity, like which doesn't make sense for a virus, because a virus will stop once it affects either everyone or it just runs out of people to infect. So over here is there's a logarithmic graph, also known as an S curve. And so basically what the S curve is if you see this right here, this is kind of like the exponential right here. It starts slightly and then it goes up to around this point right here, right? Now this point right here is to where the peak is going to be, right? Because right here you have the lowest amount of cases, and right here is going to be where your top amount of cases are. But in case of a virus, once you get to the peak of the case, it depends on the scenario. This would probably be like the worst case scenario with this is how many people it is. Then it'd form an S curve to where it evens out. So if it was something else that was a better scenario, it might look like this. Something like that, where we change the size. Well, not the size, but we change the slope angle, basically, of where it's the highest point to where it'd be the. Good evening. Hi, my name is Sam Garcia, and today I'm going to be telling you about DNA replication. Okay, so to start off with, DNA replication happens in interphase of the cell cycle. Now, this right here, this is DNA, okay? And if DNA wants to replicate, so this is basically what will happen in replication. Give me a second, I have to pull it out. Okay, so this triangle piece right here, this is helicase, right? And so basically helicase unzips the two strands of DNA, basically snipping apart the hydrogen bonds from each other. Now, while it's doing that, there is an enzyme called topomerase, which basically keeps the strands coiled up, but not too tightly compact to where like they lose genetic information, but coiled up enough. Then you have primase, which is these squares right here. These little squares right here. These are primase. And primase sets down primer. And this primer, which is more of the pink stuff right there, I color coded it so you would know. So primase sets down primer so that what was it called? Sorry about that. To where DNA polymerase, which if I switch back, is this green blob right here, this is the builder, right? So it's gonna build DNA pieces, basically replicate them, and it can only do that in a 5 to 3 prime direction, which basically means 5 to 3 primed and 3 to 5 primed. It depends on in what direction the 5 and the 3, which are the points in the carbon rings on the sugar of like in the actual DNA structure. So that'd be like 5 to 3 or 3 to 5. So it goes to a 5 to 3 direction. So this one is the leading strand because it's always going to be head is always going to be ahead of this part of the strand, which is the lagging strand. And the reason it's the lagging strand is you have the primase. It sets down part of its primer, right? And then you have the polymase, the DNA polymase, which basically starts to build up, but it's going to lag out because it can't go in that direction. So then you're going to have the primase always catching ahead, and this causes a lag, and there's some points where it's going to skip. I really couldn't draw it on here that well, but it's going to skip some points. And then you have ligase, which if I were to draw it correctly, or not correctly, but just draw something like this, right? This would be like ligase, which is basically the glue that holds it together, that holds the breaks in between together, right? Okay, so the next you would have, let's say this is your new strand of DNA after it zips back up. This is what's called semi-conservative, because part of the original DNA copied is actually going to be the new DNA strand. So this would be considered semi-conservative. And this is the whole replication process for DNA replication. Okay, bye. It was nice to see all of you.